Hello, thank you for joining us for yet another interesting webinar on architecture-driven development of embedded software systems. I'm very happy to have Thomas Schütz from Protos Software as a guest today. I've been working with Thomas since 2010, so we are going back working together since a long time. And I've been always working with him concerning architecture and optimization of toolchain. And since 2013, where he did the first training for Eclipseina in Regensburg, we've been working together also in terms of architecture training. The next training will take place in Regensburg Ettertshausen, our new office, in September, 22nd and 23rd of September. But it will be in German and it will be locally in Germany. But you have a chance to benefit from some of his know-how today in this webinar. And I'm really happy that he is sharing this know-how on architecture-driven development of embedded systems today with us. Thank you, Thomas, for doing this webinar together with us. And I'm looking forward to your technical talk. Thank you.
Thank you, Annette. Happy to be here. Welcome also from my side. Yeah, it's about architecture-driven development for embedded systems today with the method real-time object-oriented modeling. So why do we place the architecture development into the center? It's all about mastering software complexity. So if it's not complex, it's not a problem. So complexity is the only problem we have to solve. Imagine a safety problem. If you have a machine control and a big red button, if you hit the button, everything is gone, no energy anymore, no current anymore, no pressure anymore. So that's pretty easy to do. That's the standard way to do it for machine controls. You have a housing surrounded by a housing machine. That's easy to solve. It's very dangerous, but it's easy to solve the problem. So it's not complex. So it's really easy to solve. But imagine you're driving with a self-steering car with an autonomous control in your car with 200 kilometers an hour on an autobahn, on a highway, and suddenly something doesn't work anymore. Yeah, you cannot just stop the car because you still are going with 200 kilometers an hour. So it's really, really complex to get the car into a safe state again without hitting a wall or another car or something like that. So that's really complex. And that's what we need to master. So it's all about mastering software complexity. If it's not complex, it's not a problem. So now an architecture, by the way, can help us, of course, to achieve this goal. So let's have a look at the first step. So the most important question is why? So where do I want to go? Which goal do I have? What motivation does drive me? So I want to get to the blue sea here. That's where I want to go. And you see a road. So what happens if you just drive straight into the blue? You're falling down the cliff. So that doesn't help us. So what do we need in the next step? So we need to know where to go. That's the most important thing. But we need some principles, some guidelines that keep me on the road. So it doesn't help to go straight for the goal if you hit the wall on the way or something like that. So we need principles that keep me on the road. Now, I have a little pyramid here of principles and methods. Just to show you a little bit how things could be structured. So right on top, you see the why. So what are the goals? What's my reason for action? What are the top level requirements? Then beneath it, there are the architecture principles. That's what keeps me on the road. That's what makes me drive into the right direction. That helps me to stay safe. So that's things like abstraction, separation of concerns, modularity, and so on. You've heard all those concepts, but usually they are pretty much ignored in most projects. So please think about those principles. So the next level is the method level. Those methods help me to fulfill those principles. They help me to reach my goal. So if a method does not help me to reach the goal and does not help me with the principles, with any principle, then you can as well leave it away. It adds more complexity without helping you. And in the end, you think about the tools. So which tools do I need to help me with those methods? And the methods help me with the principles and the goal. So that's very important. In some cases, I see this a lot, people start to think about, so which tools do I need? So that's the wrong way to start. So if I don't even know where to go, why do I have to think about tools? So please do it the other way around. Now, let's start with the most important principle, that's abstraction. The power of abstraction. What is abstraction? I have a little example from a not software context. If I asked you to count those matches, that's usually what I do if I have the chance to get a response, not in a webinar, but in a training, for example. If I ask you to count those matches, the typical answers are 40, 100, 200, 70. So it varies a lot. But if you take the same number of matches and push them into a pattern, and that's a pattern, you can count them very, very fast. So it's 123 matches. And why can I count them so fast? Because I reduced the chaos here on the left to a certain pattern. So I reduced the information to a certain pattern. I left away the arbitrary orientation of and position of the matches. And the only purpose of this pattern is to count the matches. So you could not use it for any other purpose. Or maybe there are some purposes, but not for any purpose. But the only purpose here is to count them. So an abstraction always leaves things away, information away, in order to focus on a certain problem. So that's abstraction. So you leave things away. Now, let's have a look at a real world system. So first, again, with matches, a real software system looks more or less like that in matches. And to prove it to you, that's a UML diagram generated. So a UML class diagram. It's a bit unfair. It's a good designed system, but a flat UML class diagram doesn't help you at all. That's a relatively complex embedded system here. And you have an idea, maybe there's a class, a lot of relations here. So that's what a real world system in a flat, so in a non-abstract diagram looks like. So we need something like those abstractions. Now, why do I need abstraction? Abstraction and automation with model-driven development and tests, for example, helps you to develop faster, to test faster, and so on. So the goal is always to create an executable that does what you want it to do. That's, by the way, a STM32 code on Cortex-M executable here. On that level, that's only readable for a machine, for a computer, for a microcontroller. So we as human beings cannot work on that level, or not really. So that's why I invented high-level programming languages like C, C++, Java. That's all the same level, more or less. Object-oriented, not object-oriented, but it's the same level. We as human beings can work on that level. What we do on that level, we describe how do we do something? So step by step, what does the program need to do? Here we already get an idea. So there's a case, a switch, a state, timeout, start, stop. So this could be part of a state machine. So this explains how the program works. But what we really want to do, we want to discuss, for example, what needs to be done. And that's something you can do really good on a higher abstraction, like on a modeling language, state machines, components, sequence diagrams. That's a much higher level of abstraction. Here you can see that's a state machine. That's a blinker, on, off with the timeout in between. And that's exactly the part of the generated code. It's much bigger than that. And that's the generated executable. So what happens here is we have an abstraction step by step. From the executable, we leave away the machine details. From the C program to the model, we leave away the implementation details. So that how does the program work? I'm only interested in what. But now, if we work on that level, we still need the executable. So that's why we use code generators to generate the code from state machines, from component diagrams, and so on. Because it's really easy then to translate the C program into an executable code. So basically you can see a modeling language is nothing else than a language on another abstraction layer. And a code generator is essentially a compiler, or a compiler is a code generator. Only the level of abstraction is a different one. So that's abstraction and automation. If you work with for example, with UML tool that has no real code generator for running code, then you can work on that abstraction level, but you cannot generate the code. And if you directly program is in C program, it's really hard to get those abstractions out of the C program. So that's why we work a lot with models and code generators. That makes things really, really efficient. Now, let's have a look at the architecture in the center of the development. What happens if I put the architecture there? I can describe, first of all, the structural architecture and the behavioral architecture. Structural architecture, for example, by using component diagrams. You can see this on top here. So by double-clicking, you get into the next level of components. You can decompose things and so on. That's exactly what we want to do with a structural architecture. We want to decompose things more and more and more, separation of concerns by using different interfaces and so on. Then you can describe state machines, for example, to define the behavior of those components. So how do I start up my system? How do I shut it down? Which states do I have? Which functionalities do I have? How do I separate them in different behavioral models, in different state machines or other models? It could also be a flow model for a controller or something like that, for a motor control. So that's important to describe the behavior also on this level of abstraction. Or you could also use sequence diagrams to specify things or to log things and display them as sequence diagram to analyze your system, to debug your system. So that's important. Now, from this architecture and design diagrams, we can define the structure, the architecture. So that's where we start. And if we drill down, if we decompose things more and more, we go into the detail level design, detail level structure and behavior design. And so we can go straight to the bottom, and maybe we add some detail level code, some C code or some libraries and so on. But everything is attached to the model. Then we can generate the application, so the running application from structure and behavior, the complete running executable application. Generate them, compile it to the C code, and then it's already runnable. And then on the right leg of the V model, we can design and run software in the loop tests. So if you have components here that implement your behavior, you can also create a component that implements a software in the loop test, or even a hardware in the loop test. And you can run the software in the loop test, and later you can run the hardware in loop test on system level or on integration level, hardware software integration level, and so on. So that's very important. You can attach everything, also the test cases, to the same model. No? And to be faster and to enforce quality tests and so on, you can automate everything with continuous integration. So everything I'm going to show you is always command line capable, so you can run it headless without a graphical user interface, and just by calling the command line generator, for example, and compiler and so on. And that's very important because continuous integration helps you to be much faster and to make sure that everything is tested. And you can always deliver on any commit. That's very important. So continuous integration helps massively with the overall process. That's why it's so important to have code generators on command line. Okay, so what's the method behind all this? It's the method real-time object-oriented modeling. If you want, you can order this at Amazon and so on, but you can also get a free PDF version. It's a book we got as a present from the authors and Wiley, so the Wiley company, and we made a new version of this room book thanks to the authors and Wiley. And it's about a design of complex embedded systems. And here you can find the complete method. So please send me an email if you want a copy of this book as a PDF. Now, the eTrice toolchain, that's what we did at Eclipse, or we would do at Eclipse. We have designed the eTrice toolchain, and that's an implementation of this room method. So that's all what it's about. So usually you start to specify scenarios with a sequence diagram. So you have the components, you have the interactions, you have the states in the components. That's a specification. You cannot generate code out of it because it's not formally complete. So you cannot generate code, but it's really good to design test cases, and it's really good to specify what behavior you want. Now, the next step is to define a structure and the interfaces, ports for your components. The next step is for every component where you have behavior, you define a behavior. Can be a state machine, can also be manual code, could also be a controller, also a submodel like a Simulink model or something like that. It's always encapsulated in one of those components. They're called actors in this method. Then you generate the code, you compile it, and you run it on your embedded target. And then you can log, for example, while you're running your system, you can log sequence diagrams to have a look at the running system. So what happens? And then you iterate. That's a very fast iteration here. Depending on the size of the application, you're within code generator and incremental compilation in the range of seconds to minutes. Now, the two main concepts behind Room are the structural concepts and the behavioral concepts. Room puts for the structure the actors as in the center of development. So actor classes are hierarchical components that define the structure of a system. Yeah, you can have containment for those components, for decomposing components into subcomponents or actors, and you can also have layering to reduce massively the complexity of your system. And the ports are the only interfaces of an actor, and they define a specific role. So, for example, this actor has a functional interface for the graphical user interface, and it controls the XY controller. So it delegates something to the XY controller. So those are two different interfaces at the same component that define two different roles for this component. You could also have a control role, you could have a port, you could have a debug port. And by doing this separation of concern, this helps you a lot to reduce complexity, and especially the separation of concern. That's really, really important here. And if you drill down into the XY controller, you'll find an X-axis and a Y-axis. And we do not only have graphical editors, we also have a textual editor. So the textual editor is complete. That means you can completely program your high-level abstractions in the textual editor. But sometimes it's really good to have a graphical representation that sits on top of the text editor. But the text editor or the textual representation is very important because you can diff, merge, doing pull requests, and so on your version system, Git, Subversion, whatever you have, and it just feels like a piece of Java code or C code or something like that. But it's a higher level abstraction. So the textual editors are really important because on that level you can work, you can do the engineering, the versioning, and building libraries and things like that. That's especially for bigger systems, that's really crucial to be. Most modeling languages do have real trouble to merge models and things like that. We don't have anything of that at all because you can use the standard tooling of Git or WinMerge or whatever you want. So you don't need any special tooling for that. So that's the structural structure, and every structural component, so every actor can have a state machine or manual code or other things. The integrated modeling for the behavior are state machines. That's what we use most for those embedded systems. And state machines can also be hierarchical. They can be really deep and complex and so on. And again, here we have this textual syntax, and the graphical syntax is only sitting on top of so the graphical editors are sitting on top of the textual language. Again, you can diff, merge, and so on state machines. That's without any problems, without any special tooling. By the way, state machines are a really excellent way. So cooperating state machines are a really excellent way to get control over your embedded system, to reduce the complexity. State machine is an excellent modeling method for certain things. Now, how does this all help? Let's first have a look at the non-functional requirements. So the typical ility, scalability, testability, portability, robustness, sility, so robustness, and so on. So those are typical non-functional requirements. And by the way, the non-functional requirements are usually driving the complexity. The function is often much simpler than the problems you have with the function. So the exceptions, what happens if an error occurs? Do I not need to stop the system? How can I restart the system? So those are all non-functional requirements. So they drive the complexity. Now, the non-functional requirements, I can map them a little bit on principles. So for example, a separation of concerns helps you a lot with portability, testability, reusability, and things like that. And now the principles you can map to room features, to language features. You have, for example, the actors, the actor classes here with their ports. You have ports as interfaces, interface abstractions, state machines for behavioral abstractions, and so on. Now let's have a look at one specific example, just to give you an idea what I'm talking about. If we want to work for testability, especially separation of concerns, encapsulation, and modularity help me a lot with the testability. So if I map those to room concepts, separation of concerns, clearly an actor separates a lot of concerns here. The ports, by dividing the interfaces into several ports, you have separation of concerns, and so on. Encapsulate, or let's talk about modularity. Modularity, actors, and containment is clearly a modularity principle. The ports help you with the modularity by decoupling and cohesion. Modularity means decoupling and cohesion. Decoupling means decouple the objects so that they have a minimal set of interfaces. And the ports help really to with this modularity, because they give you a maximum of decoupling between the objects. That reduces complexity by far and enables, thanks to the modularity, also the testability. I could do this now for every non-functional requirement, and we would see that a lot of things can be helped by just using these language elements. And they're all combined in, those elements are all combined in this coherent language here in Room. Now, I give you a practical example from reality to model. So it's from the domain of medical devices. It's a production plant for medical devices. So inhalers for asthma and for if you have a problem with your lungs. So those are the inhalers. Here is a conveyor belt. And here is a little carriage that carries the parts that need to be produced. So, by the way, that's an original drawing from the designer of the machine, a schematic he did before he even started to construct the machine, to design the machine. He gave us this so that we can start to develop the software without even knowing what the real system would look like. It's only a schematic, and actually it really still works that way. Those parts, they need to be raised, and then you have here a top, or you put on the inhaler, and those tops here, they come on a conveyor belt, and so on. You have sensors, you have cylinders, so actuators, sensors, conveyor belt. Here you have sensor, analog sensor for the power, to be sure that everything is okay, and so on. So now what we did is we decomposed we decomposed the complete station here, production station. By the way, that's only a little part of the complete machine, a couple of hundred I/O points and motors and so on. And here you see, for example, that's a cylinder, that's a cylinder, that's a cylinder. We always have a reusable part here. That's a cylinder. Even if it's a linear cylinder or a gripper, it's always a cylinder. It's configurable. And if it gets more complex, I have this, for example, this component here, and you decompose it into several subcomponents. So that's a decomposition here, because that's a part. I only need this interface here for this. I only need to know, is there a new tab or not? The rest, I don't care. What's happening here behind here, I don't care. I hide it here. Separation of concerns by hierarchies, by containment hierarchy. Now, that's how we describe the structure. Now the structure is complete, and I can design the behavior. So in this component here, I have the overall behavior for the process. So get a tab here, move the cylinder down, move it up, move over there, put on the tab, measure the force, and so on. So that's step by step. Here you even see the concurrencies, if you can do things in parallel. So while I'm doing something, I already get the next part and things like that. And if I want to move a cylinder, I don't talk about IOs on this level. No, because the cylinder knows the IOs. I just give the cylinder the command, move in, move out, and that's it. So I don't have to care about IOs. We encapsulate this on a lower level. That gives you a really, really fast development process. By the way, the company is Paritech. You might know their inhalers. They are leader in Europe, and they're also a big player internationally for those inhalers. Now, what else do we do with Room? The architecture model allows you to develop a distributed real-time system. You can test them with software in the loop tests, with hardware in the loop tests, integration and system tests. You can do environment simulations with it to run your machine without attached hardware and so on. Now, the main building block is the actor for this. For many use cases, you use the actor. You use the ports for separation of concern, function, control, configuration, lifecycle, whatever. And then you can integrate different behavior languages. So state machines, that's part of Room. You can also use it to do closed loop control, to integrate closed loop control systems like a Simulink system, or so the generated code, for example, for a Simulink system, or Protos data flow language we have. Also high-level program languages like C, C++, Java, or others. Then we can integrate interfaces, for example, by adding code generators with code generators for CAN, LIN, XCP, and other standards. Then also low-level IOs for the machine controls, for example, digital, analog, all those low-level bus systems, PWM, and so on. And also high-level protocols like TCP/IP, Modbus, EtherCAT, and so on. So we all encapsulate them in an actor, and then you can use them without thinking about the technology beneath. No. And you can also use this as an integration of test and verification languages. For example, our test description language and code generators for Cage, so case generator, and for software and hardware in the loop tests. And then also we can use it to define interface contracts for model and runtime verification, so that the model already tells you that something is not okay while you're modeling. You don't even have to run it to verify statically whether the model is okay or not. Now, that's enough for the theory. I'm going to give you a little demo now. Let's jump to the development environment. It's Eclipse based, but we also have currently a beta version for Visual Studio Code. I'm using the Eclipse version. It's more complete at the moment, but we're moving fast there. Now, in the center, you have those structural editors, the structural components called actors. So inside this actor here, I have a container. It all maps to this textual language. Here you see the textual language, and you see for the exact same thing, you see the graphical language. So textual application and the traffic light container, and that's the traffic light container in the application. So now what I want to do is I want to define I want a little traffic light application. So that's my application. It's a pedestrian crossing. You have the traffic light for the car and the traffic light for the pedestrian, and a request button. So that's a minimal traffic light, as you see on every street. And I want to design the system now. First, I'm going to go into the traffic light container because I want to make it scalable. So I might need several traffic lights. So I'm already building a container and put my traffic light inside it so I can reuse the complete traffic light and not only parts of it. So now what do I need? First of all, I have a TCP/IP socket. That's a socket server here. So I need a TCP/IP client. So that's a predefined building block. TCP/IP client. It comes with the eTrice open source project. I call this socket, this component. So that's the class, that's the instance of the component here. So now I have a socket here. You see again, separation of concerns. I have a control port and a payload port. The payload port is completely independent of TCP/IP or any transport protocol. The control port not. For example, if I would use, instead of a TCP/IP connection, a UART, you could use the same payload protocol, but I would add another port for the control, because TCP/IP is configured differently from UART or other protocols. Again, reuse on any level. If you do this on every level, you reduce massively the complexity of your system. That's very, very important. So now the next level, that's something I did before that. I created a traffic light interface that translates the model languages, for example, for turning a traffic light on or off, into an ASCII code for the TCP/IP protocol. So traffic light interface, okay. So this traffic light interface starts the payload, starts the socket here over the control port, and here over the payload, we send the commands to turn on and off the lights and so on. So the traffic light interface, by the way, it's already defined as a state machine. Here you can see the state machine for the traffic light. Oh, I messed up the layout here. So you see the commands and so on. So that's the state machine for the traffic light interface. And now I want to define the logic of the traffic light. That's only the interface, on, off, and so on. So now I add the controller. That's called traffic light controller. That's an empty shell. I'm going to show you this in a minute. So that's the traffic light controller. I just added an empty shell, an empty actor. There's nothing in there. It's just a hull. So now what does the traffic light controller need? It needs a traffic light interface. So the port as an interface. Let's call this TL for traffic light interface port. It's conjugated, so it can send what the other receives and vice versa. It's an asynchronous interface, so I connect them. And now I'm already ready with my structure. I already have a fully working system, except for the behavior, because the traffic light controller does not have a behavior. So let's add a behavior. Over this TL interface, I can control my traffic light now. So let's name the state unconnected. And I'm going to, over this traffic light interface, here see all the messages you can send. I'm opening and connecting to my port 4441, because that's where my traffic light is listening. So that's a message I sent to my component underneath. And then let's go to the state car green, for example, and set the car green to true. And you see all the messages of my interface, the pad red to true. And now I'm done with my first step. So, and I get a connected from my traffic light when it's connected. That's important. Always work with answers. So don't assume that it worked. Send a message and wait for the reply. And now you know it's really connected. That's important for a robust system. So there are many, many design patterns involved here. So now I'm going to build and run the traffic light. So it's all on command line. You see, it's generated and compiled and so on. So now the room generator generates. Now it's compiled. And when it starts, I expect here that I have a green and a red light. So, okay, so that's exactly what I did. I sent a green and a red light here. And I press the request button now, but nothing happens because I have not implemented it yet. to show you what happened now on the runtime level, because obviously you did not see anything. Here, that's the sequence diagram that was generated. So it connected, then it's being connected. Then I set the car green, the pet green, and in the end, I press 2 times the request button. You can already see it, but it has no effect. You see the state of the state machine has no effect because I didn't implement it. Okay, now that's how you work with it. Now I'm going to show you a little bit more, but I'm deactivating this controller here, and I have a little cheat controller here. I implemented this, and now I have a real controller here. So that's not TL. That's called TL interface. So, okay, you see, you can completely work on this textual level. Now I have a traffic light controller again, but now the complete implementation. I can show you this in a second here. So that's the, I need to add the layouter here. That's my fault here. So now you see the completely implemented state machine for a traffic light. Now I'm going to start this again, build and run the traffic light. So now we should see no difference because it does exactly the same at the beginning. So now if I press the request button, that's the complete functionality of the traffic light. Time is a bit short for the demo. So that's basically a complete implementation of a German traffic light. So now let's quit this and have a look at the sequence diagram. Now you can see the sequence diagram is a little bit more now. If it's too much information, I could, for example, deactivate the timer service and so on. So things that I'm not interested, like the timer service and the socket, for example. Now you have the pure logic between the interface and the controller. So that helps a lot to find errors after they happen, because the logging shows you exactly what happened in your messaging system here. So now let's go on. Scalability, next, ility. We want scalability in my system, so I could now just add more references. For example, multiplicity 20. So now I would have 20 traffic light controllers. I could add 20 interfaces and so on. By doing that, I could create 20 traffic light controllers, but it's easier than that because I created a hierarchy. So I don't have to do this on a slow level. I go just one level up. So that's one level up. And on this level now I can add 20 traffic light controllers. So now I have 20 times this component. And in this component, each component has all those 3 elements. And now I can do a really nice thing. Instead of starting 1 traffic light, I'm going to start 20 traffic lights. So now I have 20 traffic lights. And when I start my traffic light controller, again, it controls 20 traffic lights or 100 or 1,000 traffic lights. So that's scalability. And of course, that's a relatively simple scalability, but you can use the same methods also to scale much bigger systems here, much more complex systems. So you see, I have 20 traffic light controllers. They all work independently. I could coordinate them to shut them down at 9 o'clock in the evening, all at the same time or whatever. So that's how scalability in Room works, just by adding more instances of the same thing. That's a really, really nice thing to have in a modeling language. So that's, by the way, that's something most modeling languages with code generators cannot do. Try this with Simulink, for example. So it's a very good language, don't get me wrong on that, but it's still, it doesn't scale very well for bigger models. Okay, so that's the normal development process. And just to give you an idea about how can we test this, I'm going to deactivate, again in the textual language, I'm going to deactivate the implementation of the behavior and of the application, and I replace it by an implementation of a test. So now I have a test container. In the test container, I add my traffic light controller, the thing I implemented before. Okay, so that's the traffic light controller, and I add it to my test case. So now that's the same traffic light controller I have shown you before, just another instance in the test case. So, and in the test case, you have a test language, and in this test language, I implement a simple test case, just a very, very simple test case. A smoke test that connects, and then it checks whether the initial lights are okay, and it presses a request button once. So exactly what I did in my graphical user interface, but now I'm doing this with a software in the loop test. So now I'm going to run this application again, and I did not start the graphical user interface because now I'm simulating everything. Oh, just a second here. So now it's running, and now I'm going to start the test case. So I'm running the test case also on command line. I can also do this with hardware in the loop. And now you see all the tests passed. Now let's have a look at the generated log. And that's now what happened between my test case and my system under test. It sent the traffic light connected, because then the system under test can move on. And the system under test replied with set car green, set pad red. That's what I expected. And set car red and set car yellow. So the system under test did this more complete than I did before. Also has been sent. So I see, I didn't expect this, but it's also not an error. I could define this also as an error, and I said anything else than what I expect, please make it an error. So I would see this as an error. And now if I change any behavior in my traffic light controller, so let's I don't know, let's make this, delete this connected here. It's the statical analysis would find this immediately, but so I wouldn't even have to run the system to find the problem here. So now I changed something, and on a continuous integration server, now I could run this test, and it would tell me immediately that something did not work. So I'm going to show you this. So I'm running the tests, and here should be failed one. Now let's update the log here, and you see immediately that it ran into a timeout while checking the initial lights. So it did not go to the right state. So I'm clicking on this on the problem, and it shows me exactly the place where the problem occurred. Okay, so that's it so far from the demo. What else can we do with this approach? I'm not going to show you a hardware in the loop test, but with the same setup I've shown you with the TOS software in the loop test, if you add a mini hill board, for example, you can place your application on this microcontroller and completely test it in exactly the same way I've shown you before, but in hardware in the loop, including all your low-level interface, digital, analog, AIOs, and so on. So, for example, the company Kercher, they are testing their complete software product line, their complete product lines, professional and home line, and so on, with the Mini Hill next to many other companies. Again, model in the center, the test cases in the center, and the structure and behavior for the environment simulation for the test cases. We generate the code, run it on the Mini Hill board. We get the loggings again. I've shown you this in software in the loop, but you also get this for hardware in the loop. And then you learn and iterate. So everything out of the same model language. You can also combine this with manual code without any problem. Something special, we also can generate combinatorial test cases. Because we have a test model, we also can use this test model to really make the test case generation much more effective. So that's it so far. I hope you enjoyed this little presentation. If you have any question, don't hesitate to contact me. And if you want any training, please contact Annette. Thanks, Annette, for the opportunity to be here. Back to you.
Yeah, we got one question. So first of all, I would like to thank you for this really very, very comprehensive information. And I think really at the end, you see, if you want to be able to test efficiently, you have to start with a good structured architecture. So everything is coming back to modeling your system at the beginning of a project, and then also all the testing will be a lot easier, and you are able to model test without a modeled architecture of your software system beforehand. It will be very difficult to do the testing at the end. So it's really important to focus on this. And I believe that Room is a very good model for this, as it's focusing on the core architectural topics you need to handle. So thank you again. And we had a question from a guy called John. He wrote us an email. Great training video on YouTube. Would love to hear about this book. Is it free? And I guess he wants to know how to get it. Yeah.
So please just send me an email at thomas.schütz@protos.de. And I'll provide you with a link, and you can download the PDF version of the book. That's free. You can also buy the paper, a copy in paper at Amazon and at Lulu, I guess it's. Feel free to send me an email, and I'll provide you with the link.
Yeah, maybe you can switch to the slide back again with your email address, and then. Or we'll just put it in the
my
chat.
Email address should. Do you not see the email address here now?
Yeah, now again. Yeah.
Okay.
Thomas.schütz@protos.de. Yeah.
Yeah, exactly.
Yeah. So thank you, Thomas, and thank you for the audience for staying until the end. I wish you a very nice remaining day. Bye.
Bye.